G'day method students. In this video we're going to have a look at rates of change, and rates of change really just mean how one quantity changes with respect to another, and mathematically and relating to what we've been studying, a rate of change is really just the gradient, and obviously with all the techniques we've been using with differentiation, we know that a lot of them really relate to just finding the gradient at a particular point. So this section's about, I guess, applications where, even though we know that often we think of gradient as rise over run, so like a vertical change divided by a horizontal change, which is also written as dy dx in a lot of cases, the variables don't always have to just be y and x, right? So the variables can actually be representing real life quantities, and so the derivative and the gradient is telling us something about how those quantities are changing. For example, dy dx is how we write the derivative when our rule's just in terms of y and x. But if you had the, say, the volume of a cylinder, and you were interested in how the volume changes with respect to the radius, well, that could be written as dv dr instead of dy dx, right? So I guess this section, as we said, is looking at how different quantities change, not just y and x, right? So it's an application here. Kinematics, which is really like the looking at movement, this is a kind of common application where we look at rates of change. And there's three kind of key words here. There's displacement. Displacement just means literally how far away you've moved from a starting position. There's also velocity, and velocity is really the rate of change of displacement. Velocity is about how quickly you're moving away from your starting position, or maybe coming back towards your starting position. So velocity is actually the rate of change of displacement, which means it's the derivative of displacement. So if you differentiate displacement, you get velocity. And acceleration is a measure of the rate of change of velocity. So it's like how quickly your velocity is changing, right? So you might be speeding up or slowing down with respect to time. And so acceleration is actually the derivative of velocity. So you can kind of, I guess, if you need to go from displacement, if you have a rule for displacement and you need to work out something about velocity, you can differentiate. And likewise, if you have a rule for velocity and you need to find out something about acceleration, you can differentiate. So let's have a look at how that works. In example one here, we've got the position. So position, meaning displacement, because position just means like how far away it is from its initial position, after t seconds is given by this rule, x of t, so x being the position or the displacement and t being time in seconds, x of t equals 3t squared minus 12t, where t is greater than 0. And we're being asked to find the average rate of change of the particle's position between t equals 2 and t equals 5. Now remember, with average rate of change, that's actually a rise over run calculation, right? So for the average rate of change of position, we're actually going to work out a y2 minus y1. Actually, I'll write it like that first. y2 minus y1 over x2 minus x1. That's kind of like your formula, but in the context of this question, that's x of 5 minus x of 2. So the notation's a little bit confusing here, but really those are our y values on top there, minus, divided by 5 minus 2, right? It's just our rise on top and our run on the bottom. But in this particular question, the rise is the change in position and the run is the change in time. And so this will be, well, let's work it out. X of 5 is 3 times 5 squared minus 12 times 5, minus x of 2, which is 3 times 2 squared minus 12 times 2, and all of that is over 5 take 2, which is 3. I haven't given myself a good amount of room here, but that's okay. So 5 squared is 75, 5 squared is 25, times 3 gives us 75, minus 60, so 75 take away 60 is going to be 15, minus 2 squared's 12, getting ahead of myself again. 2 squared is 4, times 3 is 12. 12 take away 24 gives us negative 12. This is 15 minus negative 12 over 3. And so that's actually 15 plus 12, so 27 over 3. It's going to equal 9. Now, in some cases, you just give a gradient as, you know, the gradient is 9. But in this question, we actually have units here, right? This is the average rate of change of the particle's position. So we're talking about velocity here. So when we think about back to the rise over run, remember that the rise was the change in position and the run was the change in time. And that actually gives away the units. The units are the distance over the time, right? The displacement over the time, I should say. So the units here will be the displacement was in meters, so it's meters per second. 9 meters per second is the average rate of change, or the average velocity between t equals 2 and t equals 5. For the instantaneous velocity, that's where we're going to use our derivative, right? Because we're not interested in the velocity over a period of time. We're interested in the velocity at a specific time, in this case t equals 7. And so because we now want to find out an instantaneous velocity, we need the rule for velocity. And the rule for velocity is the derivative of the rule for displacement. So if displacement was x of t, velocity will be x dash of t. Okay? And that will be, well, 3t squared, so that differentiated would give you 6t. And then negative 12t is going to just become negative 12. There's our rule for the velocity at any particular time. So when t equals 7, well, we're actually working out v of 7, which is going to be 6 times 7 minus 12. So 42 take 12 gives you 30 meters per second, right? Because velocity is a measure of distance over time. And so that's our answer. So again, a good little recap of average rate of change versus instantaneous rate of change, but also just a bit of a taste of how these three quantities are kind of related. So remember that if you've got a rule for displacement, you differentiate it and you get a rule for velocity. If you've got a rule for velocity and you differentiate it, you'll get a rule for acceleration. Moving on to one more example. It's another rates of change question, but actually this one isn't about velocity or displacement or acceleration. This one's just another two quantities that we're being given. We're told that a balloon has developed this microscopic leak and it's going to decrease in volume. So you've got a balloon getting kind of smaller and smaller and smaller as air leaks out of it. Its volume at time t seconds is v equals 600 minus 5t minus 0.5t squared. Find the rate of change of volume. Rate of change of volume, which is like the gradient of the volume. So that's going to be dv dt, right? It's going to be the derivative of the volume. Okay, so the rule for dv dt is going to be equal to, well, let's have a look at it. 600 becomes nothing. Derivative of negative 5t is negative 5. Derivative of negative 0.5t squared, well, if we multiply by the power here, we're going to get 0.5 times 2, so that's just going to be 1, and then drop 1 from the power, we're just going to be left with minus t to the power of 1. So that's our rule for the change, or the rate of change of volume at any time. So when t equals 10, after 10 seconds, when t equals 10, the rate of change of the volume is just going to be negative 5, take away 10, which is negative 15. Now again, there's units in this question, right? It was change in volume, and volume is centimeters cubed, over the change in time, and time is in seconds. So our units are centimeters cubed per second. So in other words, after 10 seconds, at that instant, the balloon's losing 15 centimeters cubed of volume every second. After 20 seconds, well, we're just going to do the same thing, but we're subbing in t equals 20. The rate of change of the volume with respect to time is going to be negative 5, take away 20, right? Because we're just subbing into this same rule here. And so that's going to be negative 25 centimeters cubed per second. Right, so after 20 seconds, it's actually losing more volume, sorry, it's losing volume more quickly after 20 seconds than what it was after 10 seconds. When will the balloon, so part B here, when will the balloon be completely flat, which means like all the air has gone out of it? Now, completely flat means that the volume of the balloon must be 0, right? Because there's no more air in it. And if we're looking at where is the volume equal to 0, well, we're not going to use the derivative because this question is not really about how quickly the air is going out of it at the moment. This question is about when is there no air in it. And so we're going to go back to the original function. And we're going to say when v equals 0, well, that just means that 600 minus 5t minus 0.5t squared is equal to 0. Now, sometimes these questions will be calculated questions, but this one's actually nice enough that it could be a non-calculated question. It looks worse than it is. Let's get rid of that 0.5 because we just don't like the look of it. So I'm going to times everything in this equation by 2, and we'll make it 1200 minus 10t minus t squared, and of course 0 times 2 is still just 0. I'm also going to kind of multiply everything by -1 and put that t squared as our first term. So let's make it t squared plus 10t, and then that 1200 would become minus 1200, and again all still equal to 0 because 0 times -1 is still going to stay as 0. Now, this is a quadratic trinomial, and that last term's 1200, which makes you like probably kind of scares you off a bit. Thinks, oh, I've got to think of two numbers that make 1200. Well, you can kind of think of two numbers that make 12, right, and add a 0 to the end of each of them. So it's not as bad as it looks, and you can use a little bit of trial and error here, but you're looking for two numbers that multiply to make -1200, so you know you need a positive and a negative number, and the two numbers have to have a difference of 10. Now, when I think of factors of 12, I think of 6 and 2, and I think of 4 and 3, and hang on a second, 4 and 3, if I make them 40 and 30, well, 40 times 30 is going to give me a product of 1200. They're 10 apart, so I think I should be able to get this to work. If I want a leftover of plus 10, I need if I want the sum to be plus 10, then I need a plus 40 and a -30, and we've actually factorized it even though it looked really bad. And of course from that, we can say therefore t equals -40 or t equals 30. And in some contexts, both of those are going to be the answers. But in this context, well, we're not talking about, time being -40 seconds. So that's not a solution that makes sense in the context of the question, but t equals 30 is. And so we could say that it's flat after 30 seconds. In other words, it takes 30 seconds for all the air to go out of this balloon. So again, just using your differentiation skills and your algebraic skills, but applying them to a context where you don't just have X and Y, you have variables that actually are applied in real life, like volume or time or displacement or acceleration and so on. Hope that gives you a good idea of how to do 10B, but again, if you need any help, make sure you contact your teachers. Cheers.